Our project is the Tandem Tilt-Wing Vertical Takeoff and Landing Unmanned Aerial Vehicle. The Quad Spray team consists of your narrator, Tyler Vargo, as Aerodynamic Design Lead, Austin Bigos as Mechanical Design Lead, Reed Goodman as Software Lead, Jessica Elliott as Electrical Lead, and Hassan Al-Kandari, who did Simulink and airfoil selection. Because of the inherent disadvantages of powered lift flight, common multi-rotors are limited in endurance, and hybrid VTOL designs are becoming common. Quadplanes, which are winged UAVs with a separate set of motors for quadcopter operations, and tilt rotors are two common solutions, but they have drawbacks we wanted to avoid. Our objective with this project was to take a different approach to VTOL UAVs. All parts that are used for vertical flight are also used for forward flight. There are no unused lift motors producing drag during forward flight, no wing blanking of motor thrust during vertical flight, and we minimize the complexity and number of tilt mechanisms. End-of-wing design has benefits in low-speed performance such as benign stall characteristics and easily allows use of the H-quadcopter configuration with no extra motor booms as seen in common quad plane and tilt rotor UAVs. It also maximizes wing area for a given span since the lifting area is divided over 4 wings instead of 2. The UAV is broken down into 3 main subsystems: propulsion, flight controls, and wing tilt. The propulsion subsystem also functions as the flight controls when in VTOL mode, with the flight controller altering motor speed to control the UAV. The flight control subsystem takes over during transition from VTOL mode to forward flight and consists of conventional control surfaces, elevators, ailerons, and a rudder. Our UAV is constructed primarily of hot wire cut foam and carbon fiber structural members. The wings were cut by hot wire around templates which were cut by water jet from plywood. Parts such as the motor mounts, wing tilt mechanism excluding spar mount, frame clamps, and nose and tail cones were 3D printed. To avoid having to test the center of gravity location with the full-size project, a simple half-scale replica was constructed of foam board and test flown with various center of gravity locations. This replica was scaled down and ballasted to have the same wing cubic loading as the full-size UAV and enabled us to confirm that the calculated center of gravity location would yield good flight characteristics. Propulsion subsystem testing showed that the motors were less efficient than expected but delivered their rated thrust with 3-bladed propellers. It was decided to use a more efficient 2-bladed propeller since the maximum thrust loss was not significant enough to be a concern. Tethered ground testing was performed before the test flights to ensure that all flight controls responded as expected. Hover testing and tuning was performed and some minor issues were discovered. Excessive frame twisting was observed, and parts have been made to remedy it. Stability was good for a completely fresh design with a lack of torsional rigidity, but more tuning needs to be done before transition flights are attempted. Forced landing was performed upon noticing one of the motor mounts was failing. There was no other damage. The motor mount failure was due to excessive heat caused by oscillations induced by the Pixhawk's auto-tuning mode. This softened the 3D printed mounts and caused them to bend. All further tuning will be done manually to avoid the repetitive oscillations that caused this issue, and the motor mount was replaced. Further testing is to come, and transition to forward flight is the next step.